From the studios of Way Happy on the south side of town, this is Mr. Meyer coming at you with two power functions. And now, what are power functions? Power functions are just that. You know what a power is, right? You have a thing called a power. It's got a base and it's got an exponent. That's a power function. Now, a lot of our power functions will have some constant k, some number in front, and that's fine and dandy. We don't care anything about that. That just helps us graph it. But it's still a power function because you have a base and you have an exponent. So therefore, it's a power, and that's your power function. And you might see some on the screen there, like circumference is a power function because it's in terms of the radius, or area is in terms of the radius squared. So all of those are power functions. They have their little constant out there, like pi. Some of power functions have positive exponents, like that one, and those are called direct variations. Others are called inverse variations because they have a negative exponent. So a negative exponent is fine and dandy. But it'll be called, a special word for that is called an inverse variation. Now, the other thing you want to know is that unless people tell you in a word problem that it's an inverse variation, then you assume it's a direct variation right there, right? You assume it's a direct variation. So let's do a quick little translation over from English to math. And what you see here is the area of an equilateral triangle varies directly as the length of the square of the sides. So that means my exponent should be positive. And so here I go. As I go to write this equation, the area of an equilateral triangle varies directly, means there's some constant here. I don't know what that is. Some constant. Directly means I'm going to multiply it with the length of the square of the sides. So I don't know, the length of the sides squared. Or maybe that would look better if I use s squared. Would that look prettier? So I'll use s as my variable, the side squared. And there is my direct variation, area in terms of side. And the k is just some number that you probably have to figure out in the problem. What about electrical currents? All right. The current I varies. Sometimes people will say proportional instead of inversely, or instead of directly, or instead of relation, right? I'm sorry, they wouldn't say it instead of inversely or directly. They're only saying instead of varies. It varies. It's inversely proportional, so that means it's inverse variation with the resistance R and the constant V. So I have a constant V, which I'm going to throw my constant down. And then R is inversely related. So R would have a negative exponent, and it looks like it's just to the first power, so -1. Or if you want, you could write it as I is V over R. And I think some of you may have seen that somewhere. So that is how I rewrite English into math. And you should be able to go the other way. You should be able to say in number one that the area of something is a direct variation of the side squared. So you should be able to go back and forth. Now, here are some common power functions that you can see. The identity, y equals x, or cubing or squaring, all ones you know, square rooting, reciprocal, right? All of those are good ones. And then here I even ask you a little quick question of like, hey, you see that one? Do you think you could write a power function for it? Let's write the equation for a power function. You can see the power function I have down there, and you try to figure out which one it is. Now, sometimes a graph helps me a ton, right? Just a visual of what's going on. So you can see at 1, it's -2. And at 4, 3, 2, 3, 4, it's -4. And at 9, it would be -6. And at 16, it would be -8. So that's not the greatest, but you can kind of see it looks like this. Or our good friend, a shooting star. So to me, this looks like a square root graph that has been flipped, right? So let's see if that makes sense. Kind of go over and take my x's and square root them and flip them. You're getting pretty close to the y values. In fact, every time you square root, it's exactly double that. So guess what? That's my power function. It is the flipping and the doubling of a square root. And that is the example of a power function. Again, how do you write that as a power function? -2x to the 1/2 power. And there it is. As a power function, I have this gorgeous graph, and I'm feeling pretty darn good. Let's ask you a question, and we'll be right back. Now let's talk about graphing power functions. And how do you graph a power function? Well, there's some things you got to know, right? Really, you look at the power. And the cool thing about the powers, think of your x squared, your x cubes. What do they look like? Well, they always have this arm going up, right? That's what they look like. So whenever you have a power that is bigger than 1, you're going to draw that arm when you're sketching. You're just doing a sketch here. And that's it. right? That's it. Think about when you have a power that is like a cube root, 1/3 power, square root, 1/2 power. You always have the shooting star arm. So that's when your exponent is between 0 and 1. If your exponent happens to be 1, well, then that's just going to be a linear function, and that's not very exciting. And then what about if you have a negative exponent? Well, a negative exponent always gives you this arm, right? So that's kind of just, again, for sketching purposes only. That's kind of something you want to know for each and every graph. And that's about what I do right here, right? I clipped this out of the book and it's beautiful. You can see that if your exponent is negative, you would have that green line. If your next exponent's bigger than 1, you'd have that red line. If it was 1, it's a black line. If it's a fraction or, between 0 and 1, then it's the blue line. And so there you have it. Now, this is neat. It tells you, hey, look, if your constant's negative, just make sure you flip it over the x-axis. But we kind of knew that already with translations. Translations, if you put a negative out front, flips it over the x-axis. All right, there's also other things that can happen in your power functions. And that is, what does the other side do? Well, you got to decide. Is it an even function? Then just reflect it over the y-axis. Is it an odd function? Then just reflect it over the origin. Or maybe it doesn't even exist. So those are your 3 options that could happen. So now what happens is somebody asked me to sketch this graph right here, right? So I'm all panicked. Oh my gosh, we're not allowed to use a calculator. This is super scary. Well, think about some of the stuff you know, right? The first thing I know is it's x to the 4th power. And if it's x to the 4th power, that means that it looks something like this on the right side. Now I notice, oh no, there's a negative out front. So let's flip this bad boy over. So it looks like this. So that's just because of the x to the 4th and the negative. Now the 2/3 does some kind of stretch and stuff. I don't know. Well, the last thing is I just want to decide, does it exist on the left side? Are there negative x's allowed in this problem? Yeah. Is it an even or an odd function would be really nice to know. Well, how do you figure out even and odd? Remember what you do for even and odds. You always plug in the negative x value. So what would I get? I would get negative 2/3 negative x to the 4th. And if it comes out exactly the same, it's even. And if it comes out exactly opposite, it's odd. Well, what would we have? We'd have negative 2/3. Then to an even power is just going to be a positive number. So x to the 4th. It would look like that. And look, that's exactly the same as the other one. So it's an even function. So what should we do with my drawing? We should copy it over the y-axis. So I should take this guy and throw it over here and say, that's about what the graph looks like. It's not a perfect graph, but it's just for sketching or maybe matching or multiple choice or whatever. That's the stuff I'm looking for. So again, let's try the next one. So look at that next one. Ooh, scary, right? Negative exponent starts us off. And so I know a negative exponent looks like that. All right, now that I got the negative exponent, if it's even, I'm going to put it over here. If it's odd, I'm going to reflect it down here. And if it's neither, I'm not going to do anything. I'm going to leave it alone, right? And so let's see what I got. Well, I'm going to put a negative x in, so it'll be 2 negative x to the negative 3. Now this one's a little confusing, so I'm going to rewrite this as 2 to the negative x to the 3rd, right? Because the negative exponent means move it down. Now I can decide what it is. Ooh, that's 2 to the negative x cubed. And now finally, if we want, we can bump it back up. But now that negative doesn't belong to the x anymore, so we can throw it out front. And we can bring the x back up. And it looks like that. And now compare this guy and this guy. Are they exactly the same? No. So that's not even. Are they exactly opposite? Yes, right? One has a positive 2, one has a negative 2. That's exactly opposite. It has a negative out front, so that's an odd function, which means we're just going to reflect this over the origin. And done. That's about what the sketch looks like. No, I don't have the 2 in consideration, that vertical stretch that's going on, but now I'm just trying to sketch and get an idea of what a graph looks like. Well, then let's try these ones, right? Let's make it a little harder. Well, all right, same rules as always. First, look at the exponent. It's 1.5. That's like bigger than 1. So what does that mean? I'm going to do something like this. It's not negative, so I don't have to flip it, so I'm feeling pretty good. Now let's see. Is it odd or even? Well, I check by plugging in a negative x and trying to figure out what the heck 1.5 is. I'm going to change that to 3/2 because decimals just grows. Fraction is so much better. Oh, what does that mean? That's 2. And then remember, when your base is 2, that's your root, and this is your power. So it's negative x to the 3rd, but it's square rooted, right? A 2 means it's square rooted. So remember, top number is your power, bottom number is your root. And so now I got that, I can figure out what the negative x cubed is. That would just be 2 square root negative x cubed. Now here comes the trouble. Can you ever square root a negative number? No, so I don't even have to worry about odd or even. This is telling me that nothing can happen here, so I won't be able to put anything to the left. I won't be able to use those negative values. So I'm done with the graph. It looks like that. All right, last but not least before we ask a question, what about this guy? All right, so again, first think about what it is. 4.4, that is the same thing as 4 over 10, or what most of us would call 2 over 5. So I think of this as negative x to the 2/5. Now that is, between 0 and 1. That's a shooting star graph. So it looks like this. Oh, wait, it's negative. So let's flip it over the x-axis. So it looks like this. And now let's just decide if it's even or odd. So if I'm going to decide that, I got to change the x to a negative x to the 2/5 power. This is going to look crazy, right? And well, what is that? That's negative the 5th root of negative x squared. Well, what is negative x squared? That's not too bad. That's the 5th root of x squared. I can take odd roots of positives or negatives, but it looks like these will always be positive. So let's clean it up a little more. Call it negative x to the 2/5 power. Well, wait a minute. That's back to the original function. So therefore, this is an even function. And if it's an even function, I should reflect it over the y-axis. So it should look like this. Crazy. That's what kind of graph I would expect. All right, let me ask you a question, and I'll be right back. All right, excellent work again. And now let's do our last thing here. We're going to model with power functions. So we're going to use our calculator and make an equation out of it. So in the stat calc, there's power regression, so you know which one to use. Your data should include 0, 0, or calculator will try to force that. So watch out for that. And then that way we'll have a model. So here I have a data that shows the distance from the sun and the period of the orbit, how many days it takes for it to make one complete orbit around the sun. And so what you'll have to do is grab your calculator and type this into, as always, this into list 1 and this into list 2. And then therefore we can use power regression. Now to save some time, I did cheat ahead because I knew you could pause the video, and I typed it in. Oh, heck, I'll go full screen. I typed it in, I hit stat, and I went to edit, and in list 1, you can see I put all the list 1 values, and in list 2, I put how many days it takes to do a full revolution. And now, let's see if a power regression is a good idea. I hit stat, I go over to calc, and I'm going to go to, I went up because it was faster, but you go down to power regression, and you hit enter, and then you hit enter on all these. And you get your calculate of your power regression, and well, bam, there it is, right? There is my power. Look at A is my base. I'm sorry, X is my base. A is my constant, and B is my exponent. So if I go ahead and now I'm going to try to transfer this over to my paper. What is that? 0.2, let's call it 0.2 x to the 1.5 power. So y equals 0.2 x to the 1.5 power. That is our power regression. So depending on x, how far away you are from the sun, I can tell you how many days it will take for you to orbit the sun. Beautiful, right? That's our power regression. And in fact, part 2 says, hey, look, if I am 4497 GMs away, I should have to look up what GMs are from the sun. How many days will it take? Well, I will just take my little equation, and I will do 0.2 times 4497 to the 1.5 power, and it will take you that many days. It will take you 60,000 days. That's how long it takes Neptune to travel around the sun. So 60,313 and a half days. 60,313.5 days takes Neptune to get around that sun. So let's call it 14 days. That's it. Have a great day. Stay happy, and I'll see you tomorrow.